So, welcome all of you. This is our second session on the topic. I'll just yeah. Okay. So this is our second discussion session on the molecular rearrangement and uh, reactive intermediate in the organic synthesis. And today, before starting this session, I will introduce myself. So this is Vijay Rane, and I am Prime Minister Research Fellow in IIT Delhi. And today we're gonna see the some of the problems on this course. So this course is taught by the Professor Shantanu Panda on the NPTL. So you all aware about this one. So in this course we are gonna discuss more about the organic intermediates and the rearrangement reaction associated with that one. So before starting the session, I would like to highlight one of the important message from the professor. So which is hope you all also have seen the same message. uh, yeah, so this is the message. So it is about uh, it is from the professor, and particularly this message convey uh, regarding the examination. So you all hopefully those who are considering this course to get some sort of certificate, so you must need to register for uh, the examination. And the examination is, as also mentioned by the professor, which is quite simple. Definitely the problems that we are going to discuss in this session, that is from the assignment, that problems are only will be in the final examination, and some problem may be based on the topic which are already covered in the lecture. So the examination will be the simple. And the next important thing that I need to highlight is that the so if you get good marks in the examination, so you will have the opportunity for 1 year project under his guidance. So this will be kind of award for you, and so you should take this as a one of the very good opportunity to work under Professor Shantanu. So you can definitely consider this opportunity. And another thing is tomorrow on the 6th August at 6 p.m. to 6:45 p.m. So there will be a discussion. The professor will be gonna join this meeting. So you definitely I mean, you try to join this one. So I believe so. Those who all have uh, uh, taken these courses on the NPTL, you should join this session as well. So. Uh, and in this session, you can directly discuss the question that you have. So you can directly discuss with the professor. So that is a very good opportunity, I can say. So you can consider that one. So this will be tomorrow, 6 p.m. and 6 p.m. to 6:45 p.m. onwards. So you also have got this mail. So just check that one. All right. So moving to the problem that we are going to discuss. So before moving to the problem, so if anyone have any doubt regarding the week two topic which are covered by the professor, particularly the structure and the stability and the molecular rearrangement of the carbon ion as a reactive intermediate, and also we have seen the Claisen rearrangement, and also different modification of the Claisen rearrangement reaction. Also, we have seen the example and application of 2,3-Wittig rearrangement reaction and 1,2-Wittig rearrangement reaction. Also, the Steven rearrangement reaction. And additionally, we have also seen the Somlet-Hauser rearrangement reaction, benzyl benzoic acid rearrangement reaction, Fauske rearrangement reaction, and so on. So hope you have already seen all the lectures on the NPTEL, and we'll move to the problems based on the topic. So if you have any doubt regarding the assignment question, you can we can discuss that one here. And I have also taken some of the examples, so we can discuss that examples as well. So before moving to this one, uh, I will just share some problems and that we'll discuss. So, right, hope my screen is visible now. So the first question is, among which of the following have the lowest pKa value? So we have given the four examples, and among them we need to answer. So which one have the lowest pKa value? So particularly this CH bond of the, so this is alkyl CH. This is like if you look at the this CH bond. So this CH is adjacent to the olefin. So this is vinylic, right? Vinyl CH bond. This is again the CH bond. In this case, particularly, there is no CH. However, it is uh, so here is the another CH. If you can check, and this is the CH bond. So which is more which is have the lowest pK value? So we need to answer this question, and we can also give the trend which has the highest pK value and all. So this pK value governed by the stability of the conjugate base formed after removal of this hydrogen. So as I have highlighted here, so these are the hydrogens that's gonna replace. So which is I will just highlight with the another color, right? So these are the hydrogen which are gonna replace, or these both are the same. So if you look at the first, so after removing this proton, so the conjugate base form is like this, and which is again doesn't have any stabilizing group. But if you look at the second uh, hydrogen, so after abstraction of that hydrogen, so this negative charge generate, which is then get the stability because of this conjugation. So in this way, it can be delocalized further in this way, and it can go up to here also. So in this way, it is getting somewhat stability, right? Because of this delocalization. The third one is the CF3 and the F. So if you look at the CF3 and the F, the CF3 is the more electron negative compared to the CF, that is the fluorine one. So uh, so if you look at the order, uh, the negatively charged, the conjugate base form after abstraction of the proton, so which has the structure. And again, in this case also, as I shown earlier, so this is how it can be delocalized throughout the system. So this again has the uh, lower pK compared to the earlier two examples. And if you look at the another, this is the stability order that I have mentioned. And another example is the one with the CF3. So that hydrogen is abstracted. Now there will be a negatively charged at this position. And now if you look at the structure, so this is the structure, and this negatively charge obviously have the similar delocalization. because of these conjugated double bonds. And again, the electronegativity of CF3 group is higher compared to the CF because is the smaller in size, and the electron pair on the this fluorine can also get involved in this bond formation. That's why this carbon is comparative electron rich than this one. So these carbons. So that's why this conjugate base has the higher stability, and as a result, so the stability of the conjugate this conjugate base is higher, and it also indicate the pKa value, that is the acidic strength of that acid is lower. So which is the acid? So the acid with the proton one, CF3, and there will be a proton. So this will be the answer. So which has the lowest pKa value. The pKa value, lower is the pKa value, more is the acidic compound. So that also you need to keep in mind. So strong acid have the lower pK value. The next question is predict the major product in this reaction. So this is the reaction we have here given, and so this again I have already mentioned here solution, but you can try to solve this before looking at directly to the solution that I have given. So the first one is the NaOH, addition of the NaOH to the alpha bromo, alpha keto. So in this one, what happens? See, so this is the keto center, and which has the alpha position. There is a bromo substituent, right? So the remaining part is the same. So what happened in presence of NaOH? So the OH, this negatively charged OH base attacks on this carbonyl carbon, further goes to here. So this will O negative. Here there is OH, which is come from the NaOH, and this is another group is remain as it is. The next from here to here, then what happens? Uh, this O negative goes back here, and further. Uh, so either this bond or this bond, which get migrated. So let's say here there is a bromo. So what happens? So this bond get negative channel back, and which further migrated to the, so attacks on this one, and bromo get removed. So basically this bond get cleaves. So this is the R group, any R group. So upon this negative charge when comes back to form double bond, C double bond O. So this bond attacks to the carbon, and the bromo get eliminated. So in the same manner, in this example also you can see. So what happens? So it has the cyclic product formation takes place upon this addition, because they are interconnected. So here, so this was the starting, right? And this is the keto. Sorry, yeah. So this is the keto, and double bond is here, and it also have the bromo group here. What happens when this NaOH attack here? So the OH minus hydroxyl group attacks to the carbonyl carbon, and it goes to the O negative. So So upon this one, so this bond get converted into the single bond. This will be O negative, and this newly added, this hydroxyl group will be here. And now this, when this negative charge O attacks back to the comes back to the to form double bond. So this entire group, uh, so this bond fuse and attacks on the bromo, and this bromo get terminated to get the final product. So which is one. So in this one you can see, if you just expand the structure, so there are two 5-member rings are formed. So the first 5-member ring is the uh, this one. So this is first, second, third, fourth, and the fifth, and similarly the second, third, fourth, and the fifth. So these are the two 5-member ring form. So this is 1, 2, 3, 4, 5. And if you look at the entire group, this is the entire group is C double bond OH group, that is the carboxylic acid group. So the answer D is the correct answer in this case. So which answer is correct? So the D answer is the correct answer in this case, because uh, this carbonyl C double bond acid group is attached at the 5-number carbon, that is in the this bond, across this bond. So this is the correct answer in this case. The next question is the stability order of the following carbanion. So the stability order here we need to mention. So before going to stability order, so we have the sp, sp2, sp3, this sort of hybridization of the carbon, and the hydrogen which is attached to the sp carbon, which is more acidic compared to the hydrogen attached to the sp2 carbon, and the hydrogen which is attached to the sp3 carbon. So in this case, the and why this is one? Because percent of S character. So the percent of S character increases, the uh, stability also increases. So in this case, we have the three examples. One is the HC triple bond C. So right, CH. The second one is the HCH double bond CHH, and another one is the CH3 C, and again CH3, right? So we need to identify. So first, we will cover multiple concepts in the same problem. So the first one is, which is the strong acid. So among this one, the first one is the strong acid compared to the second and third, and its conjugate base, that is the carbanion, which has the stability, obviously higher stability. So in this case, the first one has the higher stability, conjugated base stability. If you order stability, first one, then the second, and in the third. Also, the acidic strength of this, if you look at this, or the pK value of this, all the CH protons, the pK value also in the same, or will be in the reverse order. 2, 3. This is about pK value, because stronger acid have the lower pK value, so it will be in this on in this manner. And the reason behind that one is the percent of S character. S character stands for, uh, so we know sp3 characterization comes from sp3 characterization, hybridization means the 1s and the 3p orbitals are involved in the bond formation. So that's the sp3. The sp2 means this is how, and sp means, so this one. So if you look at the percent character of respective, so percent S character and percent P character. So in this case, percent S character is 25%, and this is 75% in the sp3 hybridization. In this case, it is 33, 66, and in this case it is about 50, and in this case it is also the 50, right? So this percentage character is higher in the sp hybridization. That's why. uh, so from this one also you can see, so the one only one orbital is involved from the s, and from the p also there is only one. So that's why it is 50%, it is kind of equal. And yes character has a more electronegative nature, because this yes character is more towards the what we can say, the center, and the p is generally in this manner, right? Either it is px, py, pz. So that's away from the center, and the more when you go more towards the center, that time electronegativity is increases. That's also one of the reason. So 5% yes character increases the electronegativity increases. That's the reason. Here also the acidity also increases in the same manner. Another question is, find the major product in the following reaction. So we have one reaction in which we have given one epoxide with the stereochemistry directing beta. So this is directing beta, that is the upward direction. So I will write the same stereochemistry. What happens when it react with the NaOH? So if you look at the more acidic proton in this case, the OH proton is more labile proton, and in presence of NaOH, what happens? It get converted into the O negative, right? So O negative, it convert into O negative, and then when you convert into O negative, it can attack backside to the this carbon, and it get open up. So what happens after the first step? So this will be remain same. So this will be the O negative in the beta direction, right? And this bond occurs again same. This the same. And if you look at the attack, so this attack will be takes place from the backside, that is from the downward side, because this is kind of yes N2 type of reaction. So the backside attack favors the attacks and the bond cleavage. That is bond formation and bond cleavage takes place simultaneously. That's the reason the stereochemistry will be inverted, and upon acidic workup, obviously the O negative abstracts the proton. So this is the stereochemistry of H. So this will be the product getting formed. So which is correct here? So the B option is the correct here in this case. Right. So the reaction, the step is SM2 manner. So that's the reason the inverted get the inverted configuration. The next question, among the following carbanion, which one is the most stable? Right. So this is interesting question. So we'll see what are the possibility for the stabilization of the each carbanion. So this is the first carbanion which has the one CO group. So if you look at the delocalized structure form after delocalization of this negatively charged inside the into the carbonyl, so we get O negative. So these two structure we get from the A. Then we have the second compound, so that's the B. And in this case, what are the possibility for the after delocalization of this negatively charged? So these are the in this case, this can delocalize in either the first carbonyl, that is on the left side, or the right hand side. So if you look at the delocalization towards the first carbonyl, so in this case, this will be the O negative. Uh, there is some comment. So sure, you can leave that one. I will upload the YouTube, the same YouTube link for this one. So you can refer the same YouTube channel as like the previously, you may have received the email regarding the uh, how to access the already recorded class. in the next question, sorry, in this one, so what happened? The first time it is delocalized on the left hand side. In the next one, what is another possibility? So from this one, if you delocalize in this the another carbonyl, so that time, so the first carbonyl will intact, and these are the uh, this was the first structure and this was the second structure is possible resonance structure by delocalization of this negatively charge. If you look at the third one, in the third one, what happened in the third one? So we have the three carbonyl now. So in the same manner, this negatively charge can delocalize on all the three, right? So this negatively charge can delocalize either this one, or this one. In the similar manner as shown in the example of this A and the B, it also have the another three structures possible, and these three structures are comes from the delocalization. On this one, I will show one example how it will delocalize. So this will be O negative. So this is the first structure. Another structure is this one another structure, and the third structure is, so now it delocalize on the this one. So the stabilized this all the it get the stabilization right by the three different resonance structure. The second one, uh, which is compared to which is higher in number. If you look at the resonance structure possible, there are the three resonance structure possible. That's why the C is the more stable compared to the B, and then compared to the A. If you just write the order of stability, then the A is the lower stable compared to the B, and again compared to the C. So this is the stability order. And if you have to select one which has the most stable carbanion, the C is the most stable carbanion in this case. Hope you got the clear answer for this one. The next question here is the predict the major product form in the following reaction. So we have given one structure and we need to identify the structure. So what happened when the starting material that we have given? So this is the starting material. It's a phenyl, and this is the upward directing hydrogen and downward directing CH3 group. So when the butyl lithium react with this starting material, what happens here? There is negatively charged is getting formed, right? And why at this position? So if you look at the this carbon which has the hydrogen, so here, so this hydrogen are comparatively more what you can say uh, labile hydrogens, because after abstraction of this proton, this carbon ion, so the carbon ion gets stability because of this delocalization at this position. So if you look at here, so this can be delocalized here, so there will be a resonance structure possible. So this will be negative, then this one, so here there is double bond O, and so on. Right. So this is the one possible structure possible for here. Another possibility is after addition abstraction of the proton on this another side, that is this hydrogen. So what is formed? So after abstraction of this proton, so after addition of this abstraction of this proton, the negatively charged form at this position. This proton also have the stability with the phenyl ring, but this is the secondary what you can say, it's tertiary carbanion. So that might be the reason this proton abstraction doesn't take place anyway. So if we move to the abstraction of this proton, move to the next step. So after abstraction of this proton, what happens? There are 1,2 Wittig rearrangement reaction. So if you look at the closely to the starting, this one, so it is 1, 2, 3, and there is again another double bond. So after 1,3-Wittig reaction, so I will just label that one for the simplicity, so it will be easy to understand. So right, so this was our carbon and form, and so this is 1, 2, and uh, this is again the same carbon. And what happens? So this bond goes to the, so goes to here. Then there will be a negatively charge. So this will be O negative in the first step, and there was again this methyl hydrogen that will be remain same, because there will be no any changes around the geometry on this one. So once this negatively charged form, so this will be 1, uh, and this is the 1, 2. So this is the second number carbon. So from this one, this carbon ion uh, attacks to the this carbon, and this bond get removed. So I will just show in the bigger structure somewhat. So what is actual reaction? So this is negatively charged, right? So what happens? This is O with the this is O, and this is the pH. So what happens? This negatively charged attacks on this carbon with to which the oxygen is attached, and this O negative O, the bond between carbon and oxygen get cleave, and it get converted into O negative. And once this and the earlier the down, so this all three groups, that is the CH3, this hydrogen, and the phenyl will be remain as it is, and also also uh, the configuration, that configuration also remains same, because if you look at the attack which is in the same direction as to the oxygen, because there is 1, 2, and 3, the geometry doesn't favor the backside attack. So in this case, the attacks will be on the same side to the CO bond. So that's why the retention in the compression, that's the important point here, is maintained. And after O negative, it is abstract the proton from the, obviously there is a aqueous workup, acidic workup. So it will abstract the proton and it get converted into the product. So which has the OH. That's the final compound, final product. So which answer correct here? So this is the one with the OH, and the hydrogen are the hydrogen methyl. This all the it will be in the same direction, and this 1, 2 rear sorry with 1, 2 Wittig rearrangement product will be the major product in this case. So why this not the product? This is because next step is the acidic workup. Then this O negative will definitely gonna abstract the proton. So this is again wrong, because also here the stereochemistry is different. Here also stereochemistry is different. Here, so after H plus, so it should convert into the OH, not O negative. So that's the wrong here. So these are wrong, and then option D is the correct answer. The next one is the one of the very well known example of from the very well known rearrangement reaction. So we have the pH C double bond O CH2 Cl, and we have added the sodium ethoxide. So what happens after abstraction of the so the sodium ethoxide, what it does, it abstracts the proton from this one, it forms the negatively charged. And once this negatively charged is getting formed, which attacks on this CH2, this Cl get eliminated, and we get a product. So in which the pH C double bond, uh, sorry, so this phenyl, then there is CH2 here double bond, and this is the product which is getting formed. And again we have the sodium ethoxide even in the solution. So this sodium ethoxide again attacks either on this side or this side, depending upon the uh, which, after attacking the site, the stability of the carbanion, the sorry, the step depend upon the electrophilic nature of the carbon. So if you look at these two centers, so the sodium ethoxide either attacks on this position or this position. So sorry. So in this case, I'll just elaborate the structure more. Right. So we have phenyl CH2 C double bond O, and this is now because this the bond is formed between the CH2 and this CH2, right? Both adjacent. Right. So this is the CH2 now because the Cl is getting eliminated. Now we have the NaOET. So which attacks on the, with how many, there are three carbons available for attack, but if you look at this carbonyl center, which is more electrophilic, so it is definitely going to attack on that position, and it attacks on the carbonyl carbon, this O negative. So I will draw with the another color, and what happens, we get a product pH C. So in this case, after attacking here, so this bond get removed, so there again negatively charged. So here what happens, so there is another CH2, this one, and then there is a double bond of OET. So this one more CH2 addition is come from this CH2. So basically this CH2 is inserted between this one, this bond, which is from starting material. So basically this CH2 is inserted between uh, the carbon atom adjacent to the carbonyl. So in this rearrangement reaction, so the step that we need to keep in mind, so we have such a starting material. So here the abstraction of proton takes place on this one. Then after abstraction, this bond goes here. So we get an intermediate step, the three-membered one, and the OET attacks here, the base, and this bond goes here. So, so now we get the additional CH2 group because of this uh, this rearrangement reaction. In this case, which option is correct? Correct here. So here the pH CH2 CH2 COET, right? So option A is the correct answer here. So what is the name of this rearrangement reaction? Anyone? So this is obviously uh, uh, hope you all have studied this in the your bachelor's. So the name of this rearrangement reaction you all must know. The next one is the find major product in the following reaction. So you have given one. This is again one type of the similar question that we have earlier seen. What happens, butyl lithium THF at minus 70 degrees Celsius. So which proton is abstract, get abstract in this case? So upon addition of this butyl lithium, so we have here one proton and here one proton. So among these two, which proton is getting abstracted? So we have seen earlier one example, this one. So this is the one. So in which we have already seen. So in this type of when such substrate reacted with the butyl lithium, what happens? So there will be 1 to Wittig rearrangement reaction, and that's the same scenario happens here. So we get a this product after 1 to Wittig, and then so you can see here. So in this case, this proton is abstracted from this one. So this is the proton. So once this proton abstracted, there will be 1 to Wittig. So this negative charge attack here, this bond go here, and this bond goes there. So there will be such intermediate strip, and we get a product. So in this one, the this O negative because of the lithium, butyl lithium. This will be O Li, and then the after uh, acidic workup, it will be OH, get converted into OH. The the main question here is the geometry of the double bond. So which geometry is from here, either cis or trans, that is, sorry, E or Z. So in this case, you can see because of this transition state, the geometry is the major one. The compound with the E geometry is the preferred compound. So in this case, so the option B is the correct option, right? So which has the E geometry, the hydroxy group addition to the phenyl CH2. This is the wrong because it had Z geometry. The E geometry driven by this transition state. So this transition state is important in this case. The next one is the how many pi electrons are present in the following species. So you have given a simple, I think this problem we have already discussed in the first lecture. So I don't think there is any need to discuss the presence of pi electron. I will just explain shortly. So in this case, just calculate 1, 2. These are the pi electrons, right? So the electrons which are involved in the double bond formation. So there is 1, 2, 3, 4, 5, 6. So 6 pi electrons are involved. So we have systems like this. So that time 4 pi electrons. So we have system. So at that time there will be a 6 pi electron. So that this type of question I don't think that really need to discuss. But so these are the option correct here. Again, the question from this one, I will just like to highlight aromaticity, anti-aromatic. So that also one of the important topic that you should have a look at. So those system which has the Horian pi electron. So that type of system is called as aromatic, sorry, anti-aromatic, and Horian plus 2 pi electron. They are the aromatic compounds. So these two also you should keep remember whether it is 4 pi electrons or pi electrons or 4 n plus 4 n pi electrons or 4 n plus 2 pi electrons. The n is 0, 1, 2, 3, anything. The next question here is the which of the indicated hydrogen in the following compound is most acidic. So you have given a structure and you need to mention so which is the most acidic hydrogen. So in this case, in this type of question, you need to identify. Sorry. Right. Then in this type of question is the draw the all the elaborated structure. So we have already given the structure, and in this one, how many hydrogens are present. So first thing we need to identify the number of hydrogens. So this is the one hydrogen which is labeled as the W. This is hydrogen which is labeled as X, and these hydrogens both are symmetrical, so which is labeled as Z, and the another hydrogen which is labeled as the Y. Uh, Someone has unmuted. Can you please mute yourself? So we have four type of hydrogens: X, Y, Z, right? Sorry, W, X, Y, Z. So among this one, so this hydrogen which is attached to the nitrogen. So we will look one by one. So this hydrogen which is attached to the nitrogen, also this hydrogen which is attached to the nitrogen, and another two type of hydrogens are again attached to the either carbons. Both are carbons, but in this one, the hydrogen Z which is attached to the carbonyl. So if you look at the structures, what are the possibility here? So this is the first one, the W. So I will just draw one by one. So what are the possibility after abstraction of the proton? So I will keep other hydrogens intact. So we'll discuss first. Right. So these are this is the N, and the after abstraction of this W proton, it will be N negative. So if you look at this structure, so this hydrogen is attached to the nitrogen. Uh, when it abstract, it will form a negatively charge on the nitrogen, and also this negative charge is adjacent to the carbonyl group. So we have two factors. It is on nitrogen and second on the carbonyl stabilization. So these are the two factors after abstraction of the proton from the nitrogen, which is labeled as a W. The second one is the, if you abstract the another, so let's abstract this. Right. So if you abstract this hydrogen, which is on the nitrogen X, so the negatively charge will be on the, again on the nitrogen, but there is no such, there is only, so which is on the nitrogen, but there is no any other stabilization factor. In the third one, that is the nitrogen which is labeled at the Z, so which is again quite clear, so which is doesn't have any kind of sorry, it has the stabilization. Right. So remaining factor will be the same here also. So after abstraction of this proton, it will form a negatively charged, which is again the stabilized by the carbonyl, right? So it has the one factor, that is the stabilization by carbonyl. And the fourth one, which is this one, so this one has the no any other stabilizing factor. So definitely this is the not most acidic. So we have neglected that possibility. So we have just neglected option C. Now, if you look at the all other options, that is the this is the one with the W. This is the one which is the X, and this is the one which is Z. So if you look at the X, so it has the stabilization only due to the nitrogen. There is no any other factors. So, but if you look at uh, the the hydrogen labeled as a W, which has the nitrogen, also this carbon N, which is again adjacent to the carbonyl carbon, right? So it also have the stabilization due to carbonyl. So there are two factors in this case. So definitely compared to the X and the W, there is the W hydrogen is the more acidic, and the next one is the one with the Z label Z. So after abstraction of the proton, so the negative charge form addition to the carbon, but there is only one stabilizing factor, that is the stabilization due to carbonyl. But if you compare between Z and the W hydrogen is the more acidic. So option A is the correct answer here. So we have the electronegative nitrogen atom and also resonance effect of the carbonyl carbon. So here we have, I already mentioned. So electronegativity of nitrogen and the resonance stabilization with the carbonyl group. So these are the two factors which stabilize this abstraction of this proton. So this NH is the more, what we can say, more acidic hydrogen. Any doubt here? All right. So if you don't have any doubt, we'll move to the next question. So the next question here is the, all right. Question on the rearrangement reaction. So here we have given the question, the predict measure the product form in the following reaction. So we have one reaction. So particularly the KH and the THF 18 crown 6. So this reaction, I hope you all remember, this is the 3,3 sigma topic Claisen rearrangement reaction, right? And the main question is the about the stereochemistry. So what is the stereochemistry in this case? So we already all know the what happens in this one. So this bond get fused and this bond is getting formed. So double bond shift to here. So there will be a like this compound. Sorry, yeah. So there is the compound which is looks like this, right? So that also that we all are aware about that one. And this is the methyl, and this is the OH. So which can further convert into the uh, double bond H, right? So this all we aware. So these are the general reaction. But what about the stereochemistry? So to understand the stereochemistry, we need to understand the reaction mechanism first, and particularly the transition states involved in this reaction. So after first step, so this KH is the basic. So it abstracts the proton, this hydride. This KH, K is the positive and the H is the negative. So that you need to remember. Otherwise, you will it will be difficult to understand. It's just like a sodium hydride, NH. It's the same. So the negatively charged form here. So what happens once this negatively charged form? This entire structure goes to the six-member transition state, and in this manner. So if you look at the stereochemistry, this O directing upward. So here also I have written the O directing upward, the hydrogen directing downward. So methyl directing downward. So here also you can see the methyl directing downward. Now there is a normal bond and another the bond is with the methyl here. So right. So these are the double bond. If you look at the lower part of the structure, so there will be again methyl with the, so here geometry is E geometry, here also geometry is E geometry. That again I have maintained here. So keep, so you can see the geometry. So the E geometry in the upper structure also and the E geometry lower part also. So this E geometry is maintained here. And now uh, that I will just discard. So you can see. So this is the E geometry, right? And this is again the E geometry. Both have the E geometry. So that are maintained in the following in the this transition state. The secondly, the hydroxy group directing upward, so which is again maintained here also. The methyl group directing downward, which is again mentioned here. So if in case this methyl is directing upward, that time where I will draw the methyl group, at that time I will draw the methyl which is here. So that you need to keep in mind. So now we have the methyl directing downward. So I have written the same manner. Now there is a C3C sigmatropic as I have said earlier. Now what happens? This 3 sigmatropic, this bond formation takes place. So this is the I will just, so this is the new bond form. Now you can see the methyl. This methyl was downward directing. So the geometry will be directing downward. Now this methyl is downward upward. So this is again upward directing. This was the alpha, and in if I just uh, label it in the more scientific term, so this was alpha. Now also you can see this alpha. The downward was the beta. This again the beta, right? Beta means directing upward. Also, if you look at the geometry getting formed after this one, this bond is the E bond, because you can see here. So this methyl, this bond and this bond. So after cleaving this bond, uh, there is again the bond, the sorry, the stereochemistry remains same. In this case, you can see there was this bond was E directing, that is trans to each other. So again it is maintained. And the next step was the again the keto enol tautomerization, that like aldehyde formation. So this is the product. And if I just draw this in this fashion, so what happens? So that you need to uh, check the stereochemistry. So now what happened? We have the this is our product. So now we need to match our answer with the options that are given. So at that time, what you can do, you can just assign the stereochemistry at each chiral center. So this is the chiral center which has the 1, 2, 3. So which is downward, sorry, this is the S stereochemistry, right? Sorry, the R stereochemistry, clockwise, right? So this is R. The next one here is the 1, 2, 3. S changes to R, right? Because this hydrogen, the fourth priority group, is directing upward. So I have just changed S, that was changes to R. I hope you all aware about how to assign the stereochemistry. So the stereochemistry for this one also R, and also the numbering. So this is the first priority group, this is second priority group, this is third priority group. So this was yes, now it changes to R because of this fourth priority group is directing upward. In the same manner, if you look at the downward structure, the first priority group is this one, the second priority group is the this entire one, and the third priority group is this one. So this will first, second, third. So it is again clockwise. That's again R. So both have the RR geometry, right? So you need to identify the structure with the RR geometry. All have the CHO aldehyde. That's again okay. Also, this is the E. So the structure doesn't have the E geometry. This structure also doesn't have the E geometry. These two have the E geometry. So I have just neglected these two options, right? Now the E geometry, here also E geometry, here also E geometry. It is there. Now we need to identify both should have the RR geometry, that as our answer. So in this case, you can see 1, 2, and 3. This is R, okay. Here 1, 2, and 3. This is again R. So answer A is the correct answer. If you look at this answer, so it should not have, it will not have, definitely not have the same configuration. So this is 1, this is 2 and 3. This is R, okay. This up to here it is okay. This part is okay, but next part is 1, 2, 3, and hydrogen is directing upward. So 1, 2, 3 changes to it, R changes to S. So this is the wrong. Option B is the wrong option. Wrong option. Option A is the correct option here. So does anyone have doubt in this question? So this is bit confusing question, but I hope uh, I'm able to explain this why the option A is the correct option, not option B, and how I have neglected the option C and D. So any doubt up to here? So if you don't have any doubt, I would just like to again highlight the notice that professor has shared. That is tomorrow. That is on the 6th of August from 6 p.m. to 6:45 p.m. The professor Shantanu will be discuss if you have any problems, and also you can directly ask any question regarding either course or in general also, you can directly ask question to the professor. So you also, this is the Google Meet link you may have received via email on the register mail ID on the NPTL, so or the SWAYAM. So the same mail ID, or either I will also copy paste on the chat box. So this is the Google Meet. Uh, so this is the Google Meet link I have already shared. So does anyone have any doubt regarding the course so that we can discuss? I have pasted the meeting link in the chat box for the tomorrow's. So you can join this meeting. So and you can directly discuss if you have any doubt with the professor also. So it will be not very often. The professor will have such meeting, but take the advantage of the schedule meeting by the professor, Professor Shantanu. So you can uh, ask any question regarding the either course or anything. You can directly discuss with them. And also, I hope he also added the in case you got good marks in the this course, you will have the opportunity for 1 year project under his guidance, and the fellowship and all the money required for this. I mean, that will be provided by NPTL or also by the Professor Shantanu. So I hope you will take advantage of this one of the very good opportunity. So all right, that's what I want to discuss today. So if you don't have any doubt, you can leave the meeting, or if you have any doubt, you can ask me. Or if you are just worried about how to ask, you can directly paste in the chat box here. So these are the some problems that we have already discussed, and there are some problems also that I will discuss either in the next week. This is another problem, which is again the similar one. And only thing is here the cyclic product is getting formed. So any doubt? Anyone have any doubt? If you don't have any doubt, you can leave the meeting, or if you just have any general question, you can ask me. I'm Please feel free to ask any question if you have, whether it is regarding the course or regarding the NPTL or anything. Mm. Sure, I will share the slide and I will also share the link for this drive. I will better share here in the chat box only.
Yeah, sure, sir. Because I have joined late, I'm unable to open the Google Meet actually, so that I have joined late. So I think the great insights, whatever you explained. I think last two problems I have seen. So I think it will be useful if you are sharing the
Yeah,
slides.
already NPTEL team haven't shared that folder link probably. Anyway, I will
Okay.
share in the chat box. Yeah. So
Yeah,
there is
sure.
one folder which contain all the slides and also the YouTube links also for the same recorded videos. So you can
Okay.
access from there also.
Yeah, sure, sure.
Yeah.
Thank you.
So this is uh, the link for the folder. Can you check whether it is able, you are able to access the link or not? So this drive link contain all the slides. So I will upload these slides also today. And again, there is the recorded. So these are the YouTube link for the earlier video, but the in the same channel you can also found the today's video as well. Generally, the NPTEL team share the link for the folder with the student, but I don't know about this time. Thank you. I will upload the today's video also and also the slides of this today's session. Yeah, thank you for joining.